Tonight, imagine a ship so far from Earth that the first passengers may never see the destination. Only their children might. In this quiet journey, we'll explore how long a generation ship could truly survive in deep space, from energy and radiation to food, repair, and human hope. Nearly 90% of viewers aren't subscribed yet. Your subscription would truly help me get closer to 1,000 subscribers. Thank you sincerely. The shortest, honest answer is this. A generation ship could survive in deep space only as long as it can keep life more organized than the universe is trying to make it. And that means the real question is not how far the ship can travel, but how long it can hold back the slow, quiet arithmetic of decay. Distance sounds dramatic because it lets the mind imagine a silver vessel crossing black oceans between the stars. But distance is almost the wrong unit of measurement here. A ship could drift for 1,000,000 years as a dead object, frozen, silent, and beautifully useless. Its hull still moving through interstellar darkness, long after the last light inside had gone out. Survival means something narrower and far more demanding. It means liquid water remains liquid in the right places. It means oxygen is produced at nearly the same rate it is consumed. It means carbon, nitrogen, phosphorus, potassium, calcium, iron, and trace minerals continue moving through living bodies, soil analogs, filters, pipes, tanks, and crops, without permanently vanishing into waste streams or toxic deposits. It means heat is moved away from machines that produce too much of it and delivered toward habitats that would otherwise become colder than any winter Earth has ever known. It means radiation does not accumulate in flesh, seeds, embryos, electronics, and memory systems faster than shielding, repair, and biological resilience can answer it. It means the ship does not merely carry people, it carries metabolism, culture, replacement parts, mathematics, medicine, law, memory, and the delicate habit of waking up each morning with a reason to keep maintaining a world no one outside can rescue. If we begin with the simplest model, a vessel stocked like an enormous pantry, then the answer is not centuries but years or decades, because stored supplies obey a cruel geometry. Every person needs a daily flow of mass and energy, and every kilogram packed at launch becomes part of a launch problem that grows brutally with scale. In orbital stations near Earth, life support systems can recycle water and remove carbon dioxide, but they still depend on resupply, replacement hardware, and a planetary industrial system beneath them. A true generation ship has no such beneath. There is no cargo craft coming up from Florida, no emergency return capsule, no ocean of spare water, no atmosphere waiting outside the hatch, no biosphere large enough to absorb mistakes. Deep space turns engineering into ecology, and ecology into timekeeping. The first boundary, then, is energy, because energy is the permission slip for order. Without it, pumps stop, lights fade, crops fail, heaters fall behind the cold, computers shut down, and the carefully separated zones of the ship begin sliding back toward the same final temperature. In physics, this is not evil, and it is not dramatic. It is simply thermodynamics doing what thermodynamics always does. A living ship must keep exporting entropy from its organized interior into the surrounding dark, and to do that for generations, it needs a power source that is dense, durable, repairable, and predictable across spans longer than most human institutions have ever remained stable. Solar power grows weak as the ship leaves the sun, not because sunlight disappears instantly, but because light spreads over area according to the inverse square law, thinning with distance until the old warmth of Earth's orbit becomes a memory. Chemical fuel is far too limited. Batteries are storage, not creation. Nuclear fission offers a more realistic reservoir, but it brings questions of fuel supply, reactor aging, radiation management, and the industrial ability to replace parts that were never meant to work for 200 or 300 years without a planet behind them. Fusion, if mastered in a compact and reliable form, changes the imagination of the problem, because its fuel possibilities are far richer. But even then, the ship must maintain confinement systems, superconductors or magnetic structures, heat exchangers, control software, and trained specialists across generations. So a generation ship is not a rocket with a bigger engine. It is a thermodynamic island, and every island survives by managing flows. The second boundary is matter, because life does not eat inspiration. Matter must circulate in loops tight enough that losses remain tolerable. On Earth, the atmosphere, oceans, rocks, bacteria, forests, farms, rivers, and weather perform this work at planetary scale, hiding the complexity from us so gently that we call it nature. On a ship, nature has walls. Carbon dioxide cannot simply drift away and become part of a forest somewhere else. Urine cannot vanish into a watershed. Dead leaves cannot disappear into soil unless there is a designed community of microbes and chemistry waiting to receive them. A closed ecological life support system must turn breath back into air, waste back into nutrients, gray water back into drinking water, and harvested biomass back into bodies without letting invisible imbalances accumulate. This is why the phrase closed system is almost misleading. No real spacecraft ecosystem would be perfectly closed because every valve leaks a little, every filter traps something, every crop removes minerals that must be restored. Every human body locks elements into bone, tissue, hair, and waste at changing rates, and every maintenance procedure creates scraps that must be recovered. The better phrase may be nearly closed, constantly corrected. The third boundary is biology, and biology is harder than machinery because it adapts, mutates, competes, and sometimes fails in ways that do not announce themselves politely. Crops under artificial light can be optimized, but optimization narrows resilience. A field on Earth has pests, fungi, bacteria, weather, genetic variation, and soil communities spread across a vast, messy world. A shipboard farm has efficiency, but also fragility. If one staple crop fails, nutrition becomes a systems problem. If pollination depends on a narrow mechanism, reproduction becomes a mechanical dependency. If microbial communities shift in hydroponic loops, food production and health can change together. Human beings are also not static passengers. They age, reproduce, learn, forget, fall in love, make mistakes, grieve, disagree, and build identities around the only world they have ever known. A journey lasting several generations must maintain a viable population, not merely a list of living individuals. Population genetics introduces another clock. Too few founders and inbreeding risk rises. Too many restrictions, and the society may feel managed like livestock. Too little planning and demographic waves can overwhelm food, housing, education, or medical capacity. A small crew can operate a mission. A generation ship requires a civilization small enough to fit inside a hull and large enough not to collapse into its own bottlenecks. The fourth boundary is radiation, the soft, invisible rain that makes deep space different from any ocean voyage in human history. Beyond Earth's magnetic field and atmosphere, energetic particles can pass through tissue and electronics, breaking molecular bonds, damaging DNA, flipping bits in memory, degrading sensors, and slowly changing materials. Shielding is not as simple as wrapping the ship in thick metal, because high-energy particles striking heavy nuclei can produce secondary radiation. So the geometry of protection matters. Water, hydrogen-rich materials, stored supplies, fuel, regolith-like mass, and layered structures become part of the architecture of survival. The safest living spaces may need to be buried not underground, but inward, surrounded by tanks, farms, stores, and structural mass, like a cave built inside a moving city. Here, geometry becomes destiny. A larger ship can place people deeper inside protective layers and distribute systems with redundancy. But a larger ship also demands more mass, more energy, more maintenance, and more internal transportation. A rotating habitat can simulate gravity through centripetal acceleration. But the radius and rotation rate must be chosen carefully, because a small, fast-spinning cylinder can disturb the human vestibular system, while a large, slow one requires enormous structure. Artificial gravity is not decorative. Over decades, weightlessness threatens bones, muscles, fluid regulation, and development, especially for children born aboard. So the ship's shape, spin, mass distribution, and internal layout become biological decisions. The fifth boundary is repair. This may be the least cinematic and the most important. A ship that cannot repair itself is already dying at launch, only slowly. Every pump has bearings. Every seal ages. Every circuit faces radiation. Every pipe can foul. Every coating can crack. Every software system can contain dormant errors. And every structural member lives under cycles of stress, heat, vibration, and microscopic impact. Carrying spare parts helps, but spare parts are just another form of stored time. Eventually, the ship must manufacture what it needs from what it has, recycling metals, polymers, ceramics, glass, semiconductors, lubricants, membranes, fibers, medicines, tools, and sensors. That means it must carry not only machines, but the machines that make the machines, and the knowledge to use them when the original builders are gone. In this sense, the true engine of a generation ship is not its propulsion system. It is its maintenance culture. Propulsion may decide whether the destination is reachable in 500 years or 5,000, but maintenance decides whether there is still a living destination inside the vessel when it arrives. So the short answer grows into a layered answer. With stored supplies only, survival might be measured in years. With advanced recycling but limited biological closure, perhaps decades, maybe longer under careful rationing and resupply-like stores. With a partly regenerative habitat, A ship might support a community for a century or two, but its risks would accumulate in the quiet places: crop disease, demographic imbalance, reactor aging, knowledge loss, material fatigue. With a large, deeply redundant world ship, shielded by mass, powered by long-lived nuclear systems, spinning for gravity, farming in controlled ecosystems, recycling nearly all critical elements, manufacturing replacement parts, and educating each generation as both citizens and caretakers, survival could move into the realm of several centuries, and perhaps, in principle, a few thousand years. But that longer answer is not a promise. It is a conditional sentence written in engineering, ecology, and human behavior. The universe does not forbid a generation ship, but it charges interest on every imperfection. Every small inefficiency compounds. Every loss of matter matters more when there is no planet to replace it. Every forgotten skill becomes a missing organ in the body of the ship. Every social fracture becomes an engineering risk because people maintain the machines that maintain the air. And so, before we ask whether such a ship could cross the gulf to another star, we have to ask whether it could preserve a tiny breathing version of Earth without Earth's forgiveness. That is the heart of the matter, quiet and immense. A generation ship could survive in deep space for as long as it can remain a world, not merely a vehicle. The moment it stops being an ecology, an economy, a school, a hospital, a factory, an archive, a garden, and a home, it becomes only a beautiful object falling through night. And in that distinction, somewhere between machinery and miracle, the real answer begins. To understand the minimum size of a generation ship, we have to let go of the image of a spacecraft as a narrow capsule with engines, seats, tanks, and windows, because that kind of machine belongs to missions that still have a home behind them and a destination close enough to define the end of danger. A generation ship is different in the most profound way. It is not primarily a vehicle crossing distance, but a small artificial world trying to remain alive while distance becomes almost irrelevant. The first clue is hidden in geometry. A small object has a large surface area compared with its volume, which means it loses heat quickly, offers little room for shielding, and gives every internal failure fewer places to hide from becoming catastrophic. A larger object, by contrast, gains interior volume faster than exterior surface area, and this simple mathematical fact, the quiet ratio between area and volume, begins to explain why a generation ship must grow beyond the scale of ordinary spacecraft. If its radius doubles, its surface area grows by a factor of 4, but its volume grows by a factor of 8. And in that extra interior space, the ship can bury living quarters behind water tanks, place farms between people and radiation, separate noisy machines from sleeping habitats, and build layers of redundancy that are impossible inside a cramped vessel. The minimum size, then, is not a single clean number, because the ship's true size is set by the functions it must contain: a habitat, a farm, a power plant, a hospital, a school, a recycling center, a repair factory, a data archive, a social landscape, and a shielded refuge against particle storms. If we imagine only a few dozen people in a metal cylinder, we may have a long-duration spacecraft, but not a civilization. If we imagine hundreds, we begin to have a crew that can reproduce and teach, but still not necessarily a society resilient enough to absorb accidents, illness, disagreement, specialization, and generational change. If we imagine thousands, the ship starts to resemble a town with enough human variety to maintain professions, traditions, medicine, governance, and genetic diversity, though even that may be fragile if the life support systems are too narrow or the culture too dependent on a few experts. If we imagine tens of thousands, the vessel moves closer to what earlier space thinkers sometimes called a world ship, a place where no single person fully understands every system, and where survival depends not on heroic astronauts, but on institutions that can outlive their founders. The history of this idea reaches back through a strange and beautiful lineage. Konstantin Tsiolkovsky dreaming of human life beyond Earth, J.D. Bernal imagining enormous spherical habitats, Gerard O'Neill proposing rotating colonies with farms and skies turned inward, and later interstellar studies treating the starship less as a rocket and more as a moving ecology. These designs were often speculative, but they forced a serious shift in thinking. Once the journey lasts longer than a human life, the ship stops being a mission and becomes a birthplace. Its walls are no longer walls around passengers. They are the horizon of childhood. Its corridors are not temporary passageways. They are streets. Its greenhouse is not cargo support. It is weather, breakfast, oxygen, and inheritance. So the minimum size has to be judged by the smallest world that can still behave like a world after many shocks. A world needs buffers. On Earth, the atmosphere is a buffer, the ocean is a buffer, the soil is a buffer, and the vastness of ecosystems gives life time to correct disturbances. In a small closed spacecraft, there is almost no buffer, only control. Control can be precise, but it is brittle. A generation ship needs both control and slack, spare oxygen capacity, spare water storage, spare crop zones, spare machinery, spare habitats, spare social room for grief, conflict, celebration, and boredom. Even the floor plan becomes a survival calculation. If everyone lives in one compact module, disease can spread quickly, fire can become a shared emergency, and psychological pressure can build without distance. If the habitat is divided into neighborhoods, sectors, and sealed compartments, failure can be isolated, but the ship becomes heavier and more complex. The same trade-off appears everywhere. More shielding protects people, but increases mass. More mass demands more propulsion energy or longer acceleration. More interior volume gives stability, but creates maintenance burden. More redundancy prevents single-point failure, but multiplies the number of components that must be inspected, repaired, and eventually replaced. The ship must therefore be large enough to be forgiving, but not so large that its own complexity becomes the dominant threat. Artificial gravity adds another layer of geometry. A generation ship cannot simply assume that human beings will flourish for generations in weightlessness, especially if children are born, bones are growing, immune systems are developing, and pregnancy is part of the social future. The most familiar engineering answer is rotation, where a cylinder, torus, or paired habitat spins so that the floor pushes upward against the feet, producing a gravity-like acceleration. The relation is simple in form. A equals omega squared times radius, but the lived consequences are not simple at all. A small radius requires a faster spin to produce Earth-like gravity, and faster spin can create stronger Coriolis effects, where turning the head or moving across the habitat produces strange sensations in the inner ear. A larger radius can spin more slowly, and feel more natural. But it demands a much larger structure with more mass, more stress, and more manufacturing difficulty. This is why many serious rotating habitat concepts are not tiny. Their scale is a medical decision, a mechanical decision, and a psychological decision at once. The geometry of the ship must make a human body feel that down is reliable, that movement is ordinary, and that growing up does not mean growing up inside a permanent experiment. Agriculture pushes the scale larger still. Calories can be calculated on paper with clean efficiency, but real diets require protein, fats, micronutrients, fiber, flavor, cultural continuity, and resilience against crop failure. Hydroponics and aeroponics can produce impressive yields, yet they require pumps, nutrients, lighting, disease control, sensors, and stable microbial management. Soil-like systems may be more forgiving in some ways, but they occupy more mass and volume and bring complexity of their own. A human population cannot live for centuries on the theoretical maximum yield of a perfect farm operating under perfect conditions, because no system remains perfect for centuries. The ship needs agricultural margin, seed banks, genetic diversity in crops, quarantine capacity, and the ability to shift diets when one food system struggles. That means the minimum size includes invisible acreage, not necessarily under an open blue sky, but in stacked growing chambers, algae bioreactors, fungal protein systems, controlled orchards, seed vaults, and nutrient recovery loops humming softly behind bulkheads. Water deepens the requirement. Water is drinking supply, radiation shield, thermal mass, industrial solvent, agricultural circulation, hygiene medium, emergency buffer, and in some designs, part of the outer armor of life. A small ship may recycle water efficiently, but a world ship benefits from having enough water mass that short-term chemical or biological imbalances can be diluted, isolated, and corrected. Heat also cares about scale. Every person, lamp, computer, reactor, motor, and biological process produces heat, and in deep space there is no air outside to carry it away. Heat must be radiated. Radiators need surface area, and surface area exposes structure to micrometeoroids, dust, thermal cycling, and maintenance challenges. So the ship's skin is not just a shell, it is part of the metabolism. It sheds waste heat into the dark the way a living creature breathes out. Protection from impacts also grows with scale and architecture. Interstellar space is emptier than any place the human senses evolved to understand, but empty is not zero. Dust grains at high velocity can strike with destructive energy. A large ship may use Whipple shields, sacrificial layers, forward bumpers, magnetic or plasma concepts in more speculative designs, and long distances between outer shielding and inner habitats. Again, depth matters. A thin-walled small craft offers little forgiveness. A larger vessel can place its most sacred spaces, the nurseries, clinics, seed banks, central archives, water cores, and command networks deep inside where the ship's own body becomes a mountain wrapped around them. Social scale is more difficult to measure, yet just as real. A few dozen people can know one another intimately, but over generations, that intimacy can become pressure. A few hundred can support more roles, but still may lack enough specialists to cover every branch of medicine, engineering, ecology, education, materials science, governance, and conflict resolution. A few thousand can sustain institutions, apprenticeship chains, artistic traditions, research groups, and overlapping skill networks, making it less likely that the death or failure of one person becomes the death of knowledge. In this sense, the minimum ship is partly a library with children inside it. It must store not only data, but the human ability to understand data. A manual is useless if no one has been trained to care why it matters. The ship must therefore include classrooms, simulations, laboratories, rituals of maintenance, and a culture where changing an air filter is not a chore beneath dignity, but a quiet act of planetary care. The most honest answer is that the smallest possible generation ship on paper may be much smaller than the smallest wise generation ship. Mathematical minimums can be made lean, beautiful, and dangerous. They assume cooperation, health, predictable births, stable machinery, efficient recycling, successful crops, and no long cascade of bad luck. A truly survivable ship must be sized not for average conditions, but for bad decades, a failed harvest, a reactor overhaul, a contagious illness, a political fracture, a lost workshop, a corrupted database, a generation less interested in engineering, a radiation storm that forces people inward, a micrometeoroid strike that closes a sector for years. That is why the ship must resemble a world, not because romance demands it, but because survival demands layers. A vehicle has systems, a world has margins. A vehicle has passengers, a world has generations. A vehicle can be optimized, a world must be allowed to breathe, change, absorb shock, and continue. Somewhere in the darkness between stars, the minimum size of a generation ship is therefore not measured only in meters, tons, or cubic volume, but in the smallest possible architecture that can hold a biosphere, an industry, a memory, and a society without outside rescue. And when we picture it correctly, it is no longer a sleek arrow flying through night. It is a slow lantern with neighborhoods turning inside it, farms glowing beneath artificial dawn, water sleeping in shielded reservoirs, machines whispering behind sealed doors, children learning the names of stars they may never reach, and an entire miniature Earth trying, very quietly, to remain Earth long enough for the future to wake up. Energy is the quiet heartbeat of a generation ship, and the moment that heartbeat becomes irregular, the ship does not instantly explode or vanish in some cinematic flash. It begins to die in layers, softly at first, almost politely, as if the darkness outside has placed one hand against the hull and started asking for everything back. The lights over the crops dim by a few %. Pumps run less often. Thermal loops become harder to balance. Air scrubbers enter emergency cycles. Data centers shed non-essential processes. Workshops delay repairs. And the ship, which once felt like a small world moving with intention, slowly reveals that every breath inside it was borrowed from a continuous flow of power. This is why energy is not merely one system among many. it is the condition that allows every other system to exist. Oxygen is not just oxygen on a generation ship, because it has to be separated, circulated, monitored, and balanced. Water is not just water, because it has to be pumped, filtered, sterilized, heated, cooled, and sent back through crops and bodies. Food is not just biology, because every leaf in the farm is also a conversion device, turning photons and nutrients into calories. And those photons must be manufactured by lamps if the ship is far from any useful sun. Even sleep is an energy event, because the room must stay warm, the carbon dioxide must be removed, the pressure must remain stable, the hull must be watched, and somewhere in the background a machine must keep deciding that morning is worth making again. The most basic physical law beneath all of this is simple and merciless. To maintain order in a closed habitat, the ship must constantly spend usable energy and export waste heat into space. Life is organized matter held away from equilibrium. A dead ship and the surrounding darkness are easy for physics to understand. A living ship is a local rebellion against disorder, and every rebellion has a cost measured in watts. The equation can be written as power equals energy divided by time, but the deeper truth is that time is the enemy inside the equation. A short mission can carry stored energy, stored oxygen, stored food, and stored patience. A generation ship cannot simply store its way across centuries, because storage is only a bridge, not a continent. Batteries may smooth peaks, flywheels may stabilize grids, chemical fuels may restart emergency systems, and thermal reservoirs may buffer the slow breathing of the habitat. But none of these solve the central problem of producing reliable energy for lifetimes after the engineers who built the first reactor are gone. Solar power, so elegant near Earth, becomes a fading memory as the ship travels outward, because sunlight thins according to the inverse square law, spreading across a larger and larger sphere until every square meter of collector receives only a small remnant of what warmed the home planet. At Mars, sunlight is already much weaker than at Earth. In the outer solar system, it becomes thin and cold. Between stars, it is nearly symbolic, useful perhaps for sensors or rare supplementation, but not for feeding a city of living bodies. A generation ship in deep space must therefore carry its own star. Not a glowing ball in the sky, but an engineered source of steady, controllable power hidden in shielded rooms where heat, radiation, and failure are treated with patient respect. Fission is the first serious candidate because it is real, dense, and understood far better than most interstellar dreams. A small mass of nuclear fuel contains far more usable energy than chemical propellant, and reactors can run for years or decades on Earth and in naval vessels. Though a ship that must endure for centuries faces harder questions than simply whether fission works. Fuel must be enriched or bred. Neutron damage slowly changes materials. Control mechanisms age. Coolant loops corrode or embrittle. Sensors drift. Shielding activates. And the trained knowledge required to operate the reactor must be renewed generation after generation. The reactor is not a magic stone. It is a living institution made of metal, mathematics, maintenance, and trust. If the ship relies on fission alone, It must either launch with enough fuel for the entire mission, create a breeder cycle that produces new fuel from fertile material, or maintain such extraordinary efficiency and redundancy that the power budget remains low enough to be plausible. None of these are impossible in principle, but none are casual. Fusion appears more dreamlike and more powerful, not because it violates physics, but because it offers an energy source connected to the same process that lights the stars. Deuterium and helium-3 are often imagined in advanced propulsion studies, while deuterium-tritium fusion is easier in some technical respects, but brings intense neutron radiation that damages structures and complicates shielding. A compact fusion system that could run steadily for centuries would transform the generation ship from a fragile ark into something closer to an artificial island with a furnace at its core. Yet such a system would still need superconducting magnets or other confinement methods, plasma control, fuel processing, heat extraction, replacement components, and a culture capable of understanding a machine that may be older than any living person aboard. Fusion would not remove the survival problem. It would move the problem upward into material science, robotics, education, and thermal management. Antimatter, black hole drives, and other exotic concepts sometimes appear at the far edge of interstellar speculation, and they are fascinating as mathematical possibilities. But for a serious generation ship, they remain less like near-term engineering and more like signposts marking how extreme the energy problem becomes when human beings ask metal to carry a civilization across cosmic distances. Yet propulsion energy and survival energy must be separated in the mind because they are related but not identical. A ship may spend an enormous amount of energy accelerating early in its journey and decelerating near the destination. But during the long middle centuries, when the stars barely shift and the passengers live out their ordinary lives under artificial dawns, the crucial demand is continuous baseload power. The engines may sleep, but the farms cannot. The navigation lasers may fall quiet, but the water pumps cannot. The main drive may be cold for generations, but the habitat grid must keep breathing every second. This baseload power must be layered like a nervous system, with primary reactors, secondary reactors, emergency batteries, local microgrids, manual bypasses, and low-power survival modes that can keep core life support alive even if whole sectors go dark. A wise generation ship would not have one heart but several, separated by distance and shielding so that no single accident can turn civilization into a sealed tomb. The power system also defines the ship's economy, because every society must decide what it can afford to do with its energy. On Earth, sunlight and fossil history made energy feel abundant to many modern cultures. But in deep space, every watt has a moral weight. How much light should crops receive for maximum yield versus long-term lamp durability? How warm should private rooms be when the ship is conserving reactor fuel? How many laboratories can run high-energy experiments while a repair crisis is underway? How much computing power should be devoted to entertainment, simulation, governance, medical research, archives, or navigation? These choices sound technical, but over centuries they become political, cultural, even spiritual. A population that grows too quickly can overrun the energy budget. A culture that treats abundance as guaranteed may become dangerous. A rigid energy authority may preserve systems but damage trust. Somewhere between austerity and waste, the ship must learn a rhythm of sufficiency, a way of living where beauty still exists, but extravagance is understood as heat that must be paid for. Heat itself is the forgotten twin of energy. Every useful process on the ship eventually becomes waste heat, and in space there is no wind, no river, no atmosphere to carry that heat away. The only final escape is radiation, the slow emission of infrared energy from surfaces into the dark. This means the ship needs radiators, perhaps enormous ones, glowing invisibly like black wings. And the size of those radiators depends on temperature, material, area, and the Stefan-Boltzmann law, where radiated power rises strongly with temperature. Run the radiators hotter and they can be smaller, but materials suffer and thermal systems become more demanding. Run them cooler and they must be larger, more vulnerable, and harder to protect from dust and micrometeoroids. Thus, a generation ship is not simply trying to make energy, it is trying to get rid of energy after using it. A reactor too powerful for the ship's radiator capacity is not a blessing, but a fever. A farm lit too intensely may grow food but strain cooling loops. A manufacturing surge may repair one crisis while creating another in the thermal balance of the hull. Energy and heat form a continuous conversation, and the ship survives only if that conversation remains calm. The deepest design challenge is therefore not maximum power, but controllable, maintainable, graceful power. A world ship does not need to sprint every day. It needs to endure. Its energy system must tolerate bad decades, imperfect operators, damaged components, changing populations, and scientific uncertainty. It must be simple enough in its essential modes that future crews can keep it alive under stress, yet advanced enough to support medicine, agriculture, industry, communication, education, and repair. It must protect people from its own radiation while using radiation to release the heat of atoms. It must preserve spare capacity without encouraging careless expansion. It must feed machines that feed plants, that feed children who will one day inherit the machines. And this is where the question of survival becomes beautifully, almost painfully clear. A generation ship remains alive only while it can keep turning stored or produced energy into organized conditions. Breathable air, clean water, edible biomass, stable temperature, functioning tools, accurate knowledge, and a society that understands the price of light. If energy becomes unreliable, the ship does not merely lose convenience. It loses the ability to argue with entropy. The darkness outside is patient beyond imagination. It can wait for a corroded valve, a failed turbine, a forgotten procedure, a damaged radiator, a political decision made too late. Against that patience, the ship offers a chain of fire, carefully passed from system to system, from engineer to apprentice, from reactor core to lamp, to leaf, to bloodstream, to memory. And so the silent heart of the vessel is not only the machine that generates power, but the long discipline of using power wisely. In the deep spaces between stars, a generation ship is alive for exactly as long as it can keep making a small, warm exception to the cold. And every soft light in its sleeping corridors is proof that for one more night, the exception still holds. The hardest part of keeping a generation ship alive may not be building the metal shell, or spinning the habitat, or even pushing it away from the sun, but persuading a small enclosed web of living things to behave for centuries like a planet that has been folded into a machine. This is the quiet center of the problem, because machines can be tested one component at a time, a pump can be rated for pressure, a valve can be replaced, a circuit can be shielded, and a reactor can be described in equations of heat, flow, and neutron behavior. But life is never just one component. Life is a conversation between gases, water, minerals, microbes, plants, animals, human bodies, waste, disease, light, darkness, decay, and renewal. And on Earth, that conversation is so immense that we almost never hear the individual voices. The forests absorb carbon dioxide without asking permission. Oceans buffer heat and chemistry on a scale beyond imagination. Soil hides entire civilizations of bacteria and fungi beneath our feet. Weather moves water from sea to cloud to river to root with a generosity that looks effortless only because the machinery is planetary. A generation ship has to replace that generosity with design. It has to take the open cycles of Earth and fold them into rooms, pipes, tanks, membranes, trays, filters, bioreactors, composters, algae columns, microbial chambers, and carefully lit farms where every atom begins to matter, because there is no outside wilderness to forgive imbalance. At the most basic level, the life support equation looks almost simple. What enters a reservoir minus what leaves it, plus what is produced inside it, minus what is consumed inside it, equals what accumulates. In engineering, this is mass balance, and it sounds calm enough to write on a whiteboard. In a generation ship, it becomes the arithmetic of survival. If oxygen production falls behind oxygen consumption, the atmosphere changes. If carbon dioxide removal exceeds plant demand in the wrong way, crops suffer. If nitrogen becomes locked in unusable compounds, protein production becomes harder. If phosphorus slowly disappears into inaccessible sludge, leaves yellow, yields fall, and the food system begins to whisper that something invisible has gone missing. The ship cannot simply store these elements forever in separate bins, because bodies are always rearranging them. A child grows bones and tissues. A tomato plant draws potassium and magnesium from nutrient solution. A crew member exhales carbon that was breakfast yesterday. A dead leaf becomes not garbage, but a temporary vault of matter that must be reopened by microbial chemistry. This is why a closed ecosystem is not a sealed jar, but a living bank, where the same limited wealth of atoms is constantly borrowed, spent, recovered, audited, and lent again. The first great loop is air, and even air is more subtle than the comforting word suggests. Human beings need oxygen, but they also need the right partial pressure, the right humidity, the right temperature, the right trace gas limits, and the absence of slowly accumulating contaminants. Carbon dioxide is not merely a waste gas, because plants require it for photosynthesis, yet too much harms humans, and too little can limit growth. Photosynthesis offers the beautiful central bargain. Light plus carbon dioxide plus water becomes sugar and oxygen. And in that reaction, a green leaf becomes a small engine of planetary memory. But the leaf is not alone. It needs nutrients, root zone chemistry, disease control, and environmental stability. It also respires, especially in darkness, returning some carbon dioxide to the air. A ship that relies on crops for oxygen must therefore manage daily rhythms of light and dark, crop age, leaf area, harvest cycles, failures, backup storage, and emergency chemical scrubbers. The atmosphere cannot be left to poetry. It must be measured molecule by molecule. Yet it also cannot be managed as if life were only chemistry, because plants under stress do not merely produce less food. They become ecological signals telling the ship that temperature, humidity, salinity, pathogens, or nutrients have drifted out of balance. The second great loop is water, and water may be the closest thing the ship has to a bloodstream. It moves through human bodies, hydroponic channels, cleaning systems, humidity condensers, cooling loops, medical rooms, and waste processors, carrying both life and trouble. Modern spacecraft already recover water from urine, humidity, and hygiene streams. But a generation ship needs more than recovery. It needs trust in recovery across centuries. Water has to be filtered physically, treated chemically, protected microbiologically, monitored for trace toxins, and kept from becoming a slow archive of compounds that no one expected to accumulate. On Earth, polluted water can sometimes be diluted by rivers or replaced by rainfall from another region. On the ship, dilution is limited by the same closed inventory. Every liter has a history. Some of it may have been sweat, then condensate, then nutrient solution, then cucumber, then soup, then blood plasma, then urine, then purified drinking water again, and this long biography is not disturbing when the system works. It is the essence of life support. The third loop is food, and food is where the mathematics of survival becomes intimate. Calories can be counted, but a human diet is not only calories. It requires essential amino acids, fats, vitamins, minerals, texture, flavor, cultural memory, and enough variation to prevent both deficiency and despair. A high-efficiency ship might grow wheat, soy, potatoes, leafy greens, algae, fungi, and perhaps insect or cell culture proteins, each chosen not because it is romantic, but because it occupies a useful place in the conversion of light, water, carbon, nitrogen, and human effort into edible biomass. Algae can grow rapidly and help process carbon and nutrients, but it may not satisfy the emotional role of food by itself. Fungi can transform plant residues into protein-rich material, but they require substrate management and strict control. Staple crops provide energy, but they take space, water, light, and time. Fresh greens provide micronutrients and psychological comfort, but their fragility makes them both medicine and risk. The ship's farm must therefore be designed less like a single perfect factory and more like a layered ecosystem of backups, where hydroponics, aeroponics, microbial bioreactors, seed banks, and waste recovery systems protect one another from the arrogance of any single method. The deepest difficulty is that life support biology has memory. A machine may fail abruptly, but ecosystems can drift quietly. A microbial community in a nutrient loop may shift toward species that clog filters or produce unwanted metabolites. A pathogen may adapt to the stable warmth of the farm. A crop variety may lose vigor if seed management is careless. A trace element may accumulate in one compartment and deplete in another. Biofilms may form in pipes, not as villains, but as ordinary life finding a surface and a gradient. Human microbiomes may change in the enclosed environment, affecting immunity, digestion, and disease transmission in ways that are still difficult to predict over many generations. This is why the dream of a perfectly closed biosphere must be treated carefully. Earth itself is not closed in energy. It is powered by sunlight and cooled by radiation to space, while its material cycles operate with huge reservoirs and immense time. A generation ship would also be open to energy, taking power from reactors or stored fuel and radiating waste heat outward. But materially, it would have to be almost closed, and the smaller the system becomes, the more sharply every fluctuation matters. Attempts on Earth to build closed ecological systems have taught a humbling lesson. It is possible to seal life inside walls for meaningful periods, but the chemistry of living systems can surprise even careful designers. Oxygen can be absorbed by materials or microbes in unexpected ways. Carbon dioxide can swing. Soil processes can dominate assumptions, and human comfort can become entangled with ecological stability. These experiments are valuable not because they prove a world ship is impossible, but because they show that the biosphere is not a machine with a few knobs. It is a dense network of feedback loops, some fast, some slow, some visible, some hiding in the dark under roots. For a generation ship, the correct design philosophy may not be total automation or total naturalism, but a disciplined partnership between engineered control and ecological resilience. Sensors must watch gases, pH, salinity, dissolved oxygen, microbial load, nutrient concentration, volatile organic compounds, crop health, water purity, and disease markers. But the system must also remain robust when sensors fail or human decisions are imperfect. Artificial intelligence may help detect patterns too subtle for exhausted crews, but it cannot replace the need for people who understand the farm as a living body. The ship needs ecologists as much as engineers, agronomists as much as pilots, microbiologists as much as navigators, and children who grow up knowing that compost is not dirtiness, but resurrection in slow motion. Waste in this setting becomes one of the most important words in the language, because waste is only matter temporarily out of place. Human feces, urine, crop residues, inedible stems, dead microbes, expired medicines, worn filters, and contaminated water streams all contain elements the ship cannot afford to lose. Yet recovering them safely is hard because pathogens must be destroyed, pharmaceuticals and hormones must be broken down, salts must be managed, heavy metals must be separated, and useful nitrogen must be returned without poisoning the root zone. The nitrogen cycle alone is almost a hidden civilization. Proteins become waste compounds, microbes transform ammonia, nitrification and denitrification must be balanced, and the system must avoid losing nitrogen as gas in ways that become expensive over centuries. Phosphorus is even more quietly precious because it has no gaseous phase that easily cycles through air. It moves through rock, soil, water, cells, bones, seeds, and waste. And if it becomes trapped in inaccessible deposits, the ship has lost a piece of its future. The ship's ecosystem must therefore be a chemical memory palace, knowing where its elements are, what forms they are in, and how to invite them back into life. And behind all this technical detail lies the emotional truth that the generation ship's garden is not decoration. It is lung, pantry, pharmacy, classroom, chapel, and clock. It tells the crew whether the ship is still balanced. It gives children something alive to touch besides other humans. It makes seasons in a place with no weather. It turns reactor power into green tissue and green tissue into breath. If the machines are the skeleton of the ship, the closed ecosystem is its metabolism. And metabolism is more fragile than steel because it survives by continuous transformation. The hardest question is not whether we can grow plants in space for a mission, because that has already begun in limited ways, but whether we can cultivate an entire chain of living renewal so stable that it does not merely function for months or years, but becomes trustworthy across births, funerals, repairs, mistakes, and forgotten assumptions. A generation ship can carry spare parts for machines, but it must carry spare pathways for life. It must be able to lose a crop without losing nutrition, lose a microbial culture without losing waste recovery, lose a sensor suite without losing understanding, lose a harvest without losing hope. That is why the closed ecosystem is the hardest problem. It is not one problem, but the place where all problems meet. Physics provides the energy. Chemistry moves the elements. Biology makes them fragile and fruitful. Engineering gives them channels. And society decides whether the living system is respected or taken for granted. In the long night between stars, the ship survives only if its small biosphere keeps forgiving it, not infinitely, but often enough. And perhaps the most beautiful image is not the engine burning in the dark, but a quiet leaf opening under artificial dawn, taking in a breath that was once human, releasing a breath that will become human again, while outside the hull there is nothing but cold starlight and time. Cosmic radiation is the kind of danger that makes deep space feel less like an empty ocean and more like an ancient invisible weather system. Because outside Earth's magnetic field and atmosphere, a generation ship is not simply traveling through darkness, it is traveling through a rain of charged particles. Rare but powerful atomic fragments, high-energy photons, and sudden storms from stars, all passing through the silence with no sound, no color, and almost no warning to the human senses. On Earth, we live inside a layered mercy. The atmosphere is a shield of mass spread above us, and the magnetosphere bends many charged particles away before they can reach the ground, so the ordinary human body never had to evolve for the raw particle environment between worlds. A generation ship, however, must become its own planet in this one very specific way. It must carry enough shielding, enough geometry, enough monitoring, enough biological caution, and enough repair capacity to keep radiation from slowly writing errors into tissue, seeds, electronics, materials, and memory across centuries. The first thing to understand is that space radiation is not one enemy, but several families of risk sharing the same darkness. There are solar energetic particles, often associated with violent events on a star, such as flares and coronal mass ejections, which can arrive in intense bursts and create a short-term hazard for astronauts if shielding is poor. There are galactic cosmic rays, high-energy particles from beyond the solar system, many of them protons, but some of them heavier nuclei, born or accelerated in extreme astrophysical environments, such as supernova remnants and other powerful cosmic engines. There are secondary particles created when primary radiation strikes the ship's hull, shielding, water tanks, or even the atoms inside human tissue. And there are ordinary electromagnetic radiations at different energies, some less concerning, some more biologically active, all of them requiring context rather than fear. The difficult class for a long voyage is galactic cosmic radiation, because it does not arrive as a single storm that can be waited out in a shelter. It is a background drizzle of energy, a thin, constant particle tide that continues while the crew sleeps, studies, gardens, ages, gives birth, teaches children, and repairs the same ship that is supposed to protect them. Radiation damage begins at scales too small to see. A high-energy particle passing through a cell can ionize atoms, break chemical bonds, and produce clusters of molecular damage. Sometimes the body repairs this cleanly. Sometimes the repair is imperfect. Sometimes the affected cell dies, which may be harmless or even protective. Sometimes a surviving cell carries a changed instruction forward, and over many years the probability of harmful outcomes rises. It would be careless to reduce this to a single simple number, because biological risk depends on particle type, dose rate, tissue sensitivity, age, sex, genetics, shielding, mission duration, and medical monitoring. But the principle is accepted. Radiation exposure beyond Earth's protection is one of the central limits on human deep space exploration. The units themselves reveal the layered nature of the problem. Absorbed dose, measured in grays, describes energy deposited per kilogram of material. But living tissue cares not only about deposited energy, but about how that energy is deposited along microscopic tracks. A heavy ion can leave dense damage along a narrow path, while a lower linear energy transfer particle distributes energy differently. So radiation protection uses dose equivalence and quality factors to compare biological effect more realistically. This is why a generation ship cannot treat radiation like a simple heat problem. Heat spreads and can be carried away. Radiation writes small local signatures into matter. Electronics experience the same quiet vulnerability in another language. A single energetic particle can flip a bit in memory, create a transient error in a processor, degrade solar cells, damage sensors, or slowly alter semiconductor behavior through accumulated dose and displacement damage. A normal spacecraft can harden electronics, use redundancy, error-correcting memory, watchdog circuits, shielding, and replacement units. But a generation ship must do all of that while assuming that every device family will eventually become old, that replacements must be manufactured or recycled, and that critical archives must remain readable long after the original storage media would have failed on Earth. Radiation therefore threatens not only bodies, but continuity. It touches blood cells and circuit boards, seeds and medical scanners, reactor controls and historical records, navigation systems, and the quiet databases where the ship stores its maps of home. The intuitive solution is to add metal, to wrap the vessel in armor and imagine safety growing with thickness, but the physics is subtler. Dense, high atomic number materials can stop some radiation well. Yet when very energetic cosmic rays collide with heavy nuclei, they may produce showers of secondary particles, including neutrons and lighter fragments, which can create their own biological hazard. Hydrogen-rich materials often perform better against certain charged particles because their light nuclei interact in ways that can reduce secondary production. So water, polyethylene, food stores, plastics, and even fuel can become part of the shielding strategy. This turns the ship's architecture into a kind of quiet geometry of protection. Living quarters should not sit against the outer hull like cabins on an ocean liner. They should be placed inward, wrapped by water reservoirs, agricultural mass, storage, waste processing systems, and structural layers, so that the most precious spaces are not merely rooms, but caves inside a moving mountain. A storm shelter would likely be smaller and more heavily shielded, a place where the population could gather during intense solar events if the ship is still within a region where its parent star can produce such events. While in interstellar space, the constant galactic background remains the larger lifetime issue. The beautiful trick is that every kilogram must do more than one job. Water is not only for drinking, it is shielding and thermal mass. Food stores are not only calories, they are radiation barriers. Wastewater awaiting treatment is not only a problem, positioned wisely, it becomes protective mass. Soil analogs, nutrient tanks, algae bioreactors, and composting chambers can all be arranged as part of a layered biological shield, if the engineers think like architects of a cave rather than designers of a shell. Yet mass has a cost. More shielding means a heavier ship, and a heavier ship demands more energy to accelerate, decelerate, maneuver, and structurally support its own rotation, if it uses artificial gravity. Here again, survival is not maximized by one heroic solution, but by a balance. Enough mass to reduce chronic exposure, enough distance from the hull to lower risk, enough storm refuge to survive bursts, enough medical screening to detect early problems, enough biological research to understand multi-generational effects, and enough redundancy to protect the machines that protect the people. There is another complication, quieter and more unsettling. Radiation risk is not only about the adults who launch, but about children conceived, born, and raised aboard. Embryonic development, childhood growth, fertility, immune function, and long-term disease risk all become part of the mission architecture. We cannot simply assume that a radiation level tolerable for a short adult mission would be acceptable for a society living for centuries. A true generation ship would likely need conservative exposure limits, careful reproductive health monitoring, seed and embryo storage in protected vaults, and perhaps genetic and cellular screening methods that raise ethical questions as serious as the engineering ones. This is where the phrase generation ship becomes heavy with meaning. It is not enough for the first crew to survive. The ship must protect people who never consented to the launch, people whose first memory may be the soft hum of ventilation and the glow of crops under artificial light. Even plant genetics matter. Seeds can suffer damage. Microbial cultures can mutate. and the agricultural system, which already balances on chemistry and ecology, must be protected from a particle environment that may slowly alter biological libraries. The ship would need seed banks stored behind thick shielding, multiple crop lineages, regular viability testing, controlled breeding, and perhaps cryogenic or low metabolism preservation for backup biological material. Cosmic radiation also shapes history by reminding us why planetary surfaces are so different. Mars, with its thin atmosphere and weak global magnetic protection, has become a natural lesson in exposure. The Moon, with no atmosphere worth speaking of, is another. Human exploration concepts for both worlds often rely on regolith shielding, lava tubes, buried habitats, or water-rich walls, because the basic truth is the same wherever the sky lacks a thick protective blanket. Life wants mass above it. A generation ship must carry that above in every direction. In a rotating cylinder, above and outside are not the same as on Earth, so the direction of shielding must be designed relative to incoming particles, structural loads, and living geometry. The outer hull may face dust and radiation. The inner rotating habitat may need layers that move with it. Cables, bearings, seals, and rotating joints must be protected without becoming impossible to maintain. If the ship uses non-rotating shield mass around a rotating living ring, engineers inherit a difficult ballet of mechanics and protection. If the whole structure rotates, the mass penalty and stress analysis become larger. Radiation is therefore not a separate chapter in the design. It seeps into everything, from shape to farming, from birth policy to data storage, from materials to ritual. The crew might come to understand storms not by thunder, but by alarms, dosimeters, shelter schedules, and the calm closing of pressure doors. Children might learn that the safest room is deep inside the ship, where the walls are thick with water and the stars are not visible. There is a sadness in that, but also a strange beauty, because the ship's body becomes an act of care. Its layers are a promise made by one generation to another. You may never stand under Earth's magnetic sky, but we have built you a hidden sky of our own. The real answer to how long such a vessel can survive is that radiation does not necessarily set a sharp deadline, like a clock striking midnight. Instead, it raises the background price of time. With poor shielding, poor monitoring, and fragile electronics, the price becomes too high quickly. With deep shielding, storm shelters, hardened systems, medical vigilance, protected biological archives, and architecture that uses every reservoir and storehouse as part of a defensive geometry, the price can be reduced enough that other limits may become more important. But it can never be ignored, and it can never be wished away by the romance of interstellar travel. Deep space is not empty. It is crossed by messages from exploding stars, restless suns, and violent cosmic histories, and every message carries energy. A generation ship survives by learning to listen without being destroyed, by placing its gardens behind water, its children behind gardens, its archives behind stone-like mass, and its hopes behind layers of patient design. And in the long dark between stars, while the hull receives the invisible rain of centuries, the measure of civilization may be this: whether a small, warm world can keep its people softly breathing inside a cave it built for itself, while the universe continues, quietly and endlessly, to fall against the walls. A generation ship does not only have to keep human bodies alive, it has to keep humanity from narrowing quietly and invisibly until a future population becomes a small echo of the people who first stepped aboard. This is one of the most delicate questions in the entire idea of interstellar travel, because population sounds like a simple number from a distance, as if the designers could write 100 or 1,000 or 10,000 into a mission plan and seal the matter forever. But a living population is never just a head count. It is a moving pattern of births, deaths, health, age structure, fertility, inherited variation, accidents, choices, culture, memory, and time. A ship with 100 people and the wrong age distribution can be more fragile than a ship with fewer resources but a wiser demographic structure. A ship with enough genetic diversity at launch can still lose it through poor reproductive planning, disease, random chance, or social collapse. A ship with perfect mathematical planning can still fail if people come to feel that their lives have been reduced to variables in a breeding schedule, because on a world ship, biology and dignity cannot be separated without consequences. The first layer is the most basic population question. How many people are required to operate the ship today? That number includes engineers, doctors, farmers, ecologists, teachers, reactor specialists, materials technicians, programmers, navigators, machinists, caregivers, and administrators. But if the journey lasts centuries, the deeper question is not who can operate the ship today, but who can teach the next people to operate it tomorrow. A generation ship needs overlap. It needs apprentices learning before elders disappear. It needs enough specialists in each critical field that the loss of one person does not become the loss of an entire discipline. It needs doctors who can train doctors, farmers who can train farmers, and engineers who can explain not only which procedure to follow, but why the procedure exists. Because blind obedience to old manuals may preserve a system for a while, yet true survival requires understanding that can adapt when the manual no longer matches the failure. This alone pushes the minimum population upward, away from the romantic image of a tiny chosen crew and toward something more like a town, perhaps eventually a city, moving under artificial stars. The second layer is genetics, and here the ship enters a quieter mathematics, one that has shaped life on islands, in endangered species, and in small human communities throughout history. Every person carries 2 copies of most genes, one from each parent, and populations preserve diversity through recombination, mutation, and the mixing of family lines over time. If the founding group is too small, relatives become more likely to have children with relatives over generations, and harmful recessive traits, usually rare and hidden in larger populations, can appear more often. The technical term is inbreeding, but the real issue is the loss of options. A diverse population is like a library with many versions of possible futures. A narrow population is a library where too many shelves hold the same book. Genetic drift adds another slow force. Even without deliberate selection, random changes in who has children and how many can make some gene variants disappear forever, especially in small populations. This is not because anyone makes a bad choice. It is because randomness has more power when the sample is small. In population genetics, effective population size is often more important than the census number, because a ship may contain many people, but if only a smaller subset contributes genetically to the next generation, the true genetic size of the population shrinks. Unequal family sizes, uneven sex ratios, infertility, early deaths, reproductive delays, cultural restrictions, or social divisions can all reduce effective population size, even when the corridors feel crowded. A careful planner, therefore, cannot simply ask how many people are aboard. They must ask how widely ancestry is distributed through time. Some mathematical studies of multi-generational interstellar travel have explored surprisingly low numbers under controlled assumptions, sometimes suggesting that a population below a few hundred could, in a model, avoid severe genetic trouble if reproduction is carefully managed and the journey is not too long. But those models depend on assumptions that should be treated with humility. Low accident rates, stable health, good records, cooperative society, balanced births, and medical control over inheritance. If the ship is meant to survive not merely on paper, but through bad decades, crop failures, epidemics, political tension, mechanical crises, and human unpredictability, the wise number grows. Several hundred may be a theoretical lower boundary under strict management. A few thousand begins to feel more resilient. Tens of thousands would be safer for cultural, professional, and genetic diversity, though that also makes the ship larger, heavier, more energy-hungry, and more complex to govern. This is the central trade-off. A small population is easier to house and feed, but easier to lose. A large population is biologically and culturally stronger, but demands a larger artificial world. There is no free number. Every person is both a life to protect and a system demand to support. Age structure is another hidden clock. A ship cannot launch with everyone the same age, because then it inherits a demographic wave, a large group aging together, retiring together, needing care together, and eventually dying within the same broad window. A stable society needs a steady distribution of ages, with children, young adults, mature workers, elders, and teachers all present in balanced proportions. If births happen too quickly, the ship may exceed food, space, education, and medical capacity. If births happen too slowly, the workforce shrinks, knowledge transmission weakens, and the society becomes top-heavy with age. If a disaster removes many people in one cohort, the effect can echo for generations. On Earth, migration can repair demographic gaps. On a generation ship, there is no neighboring valley, no distant city, no new population arriving by sea. The ship must produce its own continuity. That makes reproductive planning unavoidable, but also morally sensitive. The crew are not livestock, and their children are not mission equipment. Any sustainable system would need to balance individual freedom with the hard limits of air, food, space, and genetic health. Perhaps through transparent governance, voluntary family planning, long-term demographic education, and social norms built around stewardship rather than coercion. A ship that preserves biology by damaging human dignity may survive mechanically while failing as a human project. Modern technology might soften some limits. Cryopreserved embryos, sperm, eggs, stem cell lines, or genetic archives could expand the founding genetic library without requiring all donors to be awake or even aboard as living adults. This idea is powerful because it separates genetic diversity from immediate population size, allowing a smaller active crew to draw from a larger biological archive over time. Yet it does not erase the deeper questions. Who chooses when archived genetic material is used? Who counts as an ancestor in a society where some children may inherit biology from people who never walked the corridors? How are records protected from corruption, politics, taboo, or forgetting? How does the ship prevent a genetic archive from becoming a sacred relic no one understands well enough to use safely? Assisted reproduction, genomic screening, and future medical tools could reduce certain inherited risks, but they would also require ethical frameworks that remain stable across centuries, and in a closed society, ethics is not decoration, it is infrastructure. The population must also remain healthy in ways that are not purely genetic. A generation ship is an enclosed disease environment. Pathogens may be controlled more tightly than on Earth, but the microbiome of the population could also become less diverse. Immune systems shaped by a narrow microbial world may change across generations. Nutritional limitations, radiation exposure, stress, artificial gravity levels, sleep cycles, and limited environmental variation could all influence development in subtle ways. If the ship's society becomes too isolated biologically, it may grow vulnerable to internal microbial shifts or to conditions at the destination, if contact with a planetary environment ever occurs. For this reason, biological preservation may need to include not only human genomes, but microbial libraries, crop diversity, animal or cell culture systems, medical cultures, and a disciplined understanding of symbiosis. Human beings are not single organisms in the simple sense. Each person is a walking community of human cells and microbial partners, and a generation ship must carry that hidden ecology carefully. Social genetics, if we can call it that, matters just as much. A population can be genetically diverse and still become culturally narrow. If children are taught only maintenance and obedience, curiosity may fade. If conflict is suppressed rather than resolved, resentment may become hereditary in a social sense, passed down as family memory. If certain groups control reproduction, education, or technical knowledge, the ship may fracture into classes, and class division aboard a closed vessel is not only unjust, it is dangerous, because the air does not respect hierarchy. The people who repair filters, grow food, teach children, maintain reactors, care for the sick, and preserve archives all hold pieces of survival. A resilient population needs distributed competence. It needs more than enough people. It needs enough trust moving among them. Here, the minimum number becomes almost impossible to reduce to arithmetic. You need enough genetic lines to avoid biological narrowing, enough professions to avoid technical narrowing, enough teachers to avoid intellectual narrowing, enough storytellers to avoid spiritual narrowing, and enough ordinary friendships to keep the ship from feeling like a prison with a mission statement. The answer to how many people are enough is therefore layered. For a short and tightly controlled multi-generational model, perhaps a surprisingly small number might remain mathematically viable. For a real ship meant to absorb centuries of uncertainty, several hundred is likely a dangerous floor. A few thousand is more plausible, and a much larger population would be wiser if mass, energy, agriculture, and governance can support it. But the deepest answer is that no founding number is enough by itself. A generation ship survives by maintaining effective diversity over time. Genetic diversity, age diversity, skill diversity, cultural diversity, ecological diversity, and moral diversity strong enough to keep asking difficult questions before the ship becomes too small in mind. In the darkness between stars, humanity would not shrink all at once. It would shrink by losing a family line here, a forgotten craft there, a crop variety, a medical specialty, a language of care, a habit of patience. The task is to prevent that quiet narrowing. And so, in the sleeping heart of the vessel, beside the seed vaults and medical archives, beneath the soft lamps of nurseries and classrooms, the most precious cargo may be variation itself. Many ways to be human, many ways to remember, many hands ready to repair the same fragile world. And enough future inside the population that the ship does not merely arrive somewhere, but arrives still wide enough to become a civilization. A generation ship can be launched by engines, but it can only survive by maintenance, because the true lifetime of such a vessel is not measured by how long its hull can drift through space, but by how long its civilization can keep finding, understanding, repairing, remaking, and improving the thousands of quiet things that fail without ceremony. In the imagination, interstellar travel often belongs to propulsion. The bright departure burn, the slow acceleration, the beautiful leaving of the sun behind. Yet for a ship meant to live across centuries, the grand engine may become almost secondary during the long middle night, while the small systems become everything. A bearing warms by 1 degree more than expected. A pump vibrates in a pattern too faint for human ears. A seal becomes slightly less elastic after years of temperature cycling. A radiator panel develops a hairline fracture after being struck by dust no larger than a grain of smoke. A memory module records an error, then another, then an error in the system that was supposed to correct the error. None of this feels like catastrophe at first, and that is why it is so dangerous. Catastrophe on a generation ship is often not one dramatic event, but a chain of neglected tolerances, each one small enough to postpone until the ship discovers that postponement has become a kind of debt. On Earth, civilization survives this problem by leaning on a vast planetary supply chain. Mines, factories, ports, warehouses, universities, repair shops, semiconductor plants, chemical refineries, machine tool industries, transport networks, and millions of specialists who may never meet but whose work quietly supports one another. If a hospital scanner breaks, a replacement part can arrive from another continent. If a water plant needs a valve, it can be ordered. If a reactor needs a specialized alloy, that alloy belongs to an industrial ecology spread across nations. A generation ship has no continents behind it. It cannot order a pump from Earth 200 years after launch. It cannot wait for a factory on the home planet to remember it. If the ship carries every spare part it may ever need, the mass becomes enormous. And even then, the plan remains fragile, because designers cannot perfectly predict all failures across centuries. Spare parts are only frozen maintenance. Eventually, the freezer empties. The ship must therefore carry the ability to make parts, and deeper than that, the ability to make the tools that make parts, and deeper still, the knowledge to recreate a manufacturing chain when some part of that chain itself breaks. This is the threshold where a spacecraft becomes a miniature industrial civilization. A normal mission needs redundancy. A generation ship needs regeneration. It must recycle metals, polymers, ceramics, glass, carbon composites, lubricants, membranes, insulation, electronics, optical fibers, catalysts, batteries, sensors, filters, medical devices, and structural materials, not once, but repeatedly, with losses kept low enough that the inventory of useful matter does not quietly bleed into unrecoverable waste. The math is simple in shape and merciless in consequence. If a critical material is lost at even a small percentage per cycle, over many cycles the remaining stock falls toward scarcity. And scarcity aboard a closed ship is not merely economic, it is existential. A gram of rare catalyst, a wafer of semiconductor material, a trace element needed for electronics, a polymer additive required for seals, or a sterile membrane in a water processor can become as precious as gold, not because it is beautiful, but because something else cannot live without it. Maintenance begins with knowing what is happening before failure becomes visible, so the ship must be filled with sensing, diagnostics, and prediction. Vibration analysis can reveal bearing wear. Acoustic signatures can reveal leaks or cavitation. Thermal imaging can reveal electrical resistance, insulation loss, or coolant imbalance. Spectroscopy can monitor air, water, and industrial streams. Strain gauges and fiber optic sensors can watch structural loads. Radiation dosimeters can track environmental exposure. Machine learning systems may find patterns across decades of data that a single crew could never see. But prediction is not wisdom unless the society knows how to act on it. A warning ignored because of politics, fatigue, denial, or lack of spare capacity is only a prophecy written in red. The ship must develop a culture where maintenance is not considered inferior to exploration, because exploration may be the reason the ship departed, but maintenance is the reason it is still alive. In that culture, the hum of inspection robots in distant service tunnels would be as sacred as bells, and the people who crawl behind panels, clean biofilms from pipes, replace seals, calibrate spectrometers, anneal metals, and rebuild pumps would not be background labor. They would be the immune system of the world. Materials science becomes one of the ship's quiet forms of medicine. Metals fatigue when stresses repeat. Welds and joints age under load. Polymers outgas, harden, crack, or lose flexibility under radiation and time. Lubricants degrade, especially in vacuum, radiation, and temperature extremes. Electronics suffer from single event effects, cumulative radiation dose, electromigration, thermal cycling, and the simple historical fact that no digital architecture remains naturally immortal. Even if the outer hull is never catastrophically pierced, the ship is still being rewritten atom by atom. Micrometeoroids and interstellar dust add another layer of patient violence. At high relative speeds, tiny particles can carry enough kinetic energy to pit, puncture, vaporize, or erode exposed surfaces. So forward shields, sacrificial layers, Whipple structures, standoff distances, and perhaps more speculative electromagnetic or plasma defenses must be inspected and renewed. The outer body of the ship is not a permanent wall. It is skin, and skin must heal. That healing may require robotics, because many repairs will occur in places too dangerous, too cold, too radioactive, too external, or too repetitive for human crews. Yet robots do not remove the maintenance problem. They join it. They need joints, motors, sensors, software, power, spare parts, and repair facilities of their own. A civilization that says, the robots will fix it, must also answer, who fixes the robots? Who manufactures their actuators? Who audits their code? Who prevents a hidden software dependency from becoming a single point of failure? And who teaches the next generation the difference between automation and understanding? Additive manufacturing, often imagined as a miracle of self-sufficiency, is powerful but not complete. A 3D printer can shape certain materials, but it still needs feedstock of known purity, energy, print heads or lasers, calibration, post-processing, heat treatment, surface finishing, inspection, and design files that are correct for real loads, not just approximate shapes. A printed bracket may be easy. A radiation-hardened microprocessor, a high-performance turbine blade, a medical-grade implant, or a long-life vacuum seal is far more demanding. Subtractive machining, casting, sintering, chemical vapor deposition, crystal growth, lithography, metallurgy, polymer synthesis, and precision metrology all become pieces of the ship's industrial body. The deeper the supply chain, the more the ship resembles a moving city with a factory district hidden behind the gardens. It may need foundries small enough to fit inside its mass budget, clean rooms for electronics, biolabs for medicines, workshops for tools, recycling plants for alloys, chemical reactors for polymers, ceramic kilns, glass processing, spare sensors, calibration standards, and archives of designs that include not only finished products, but the processes needed to reproduce them from available materials. The historical lesson is humbling. Advanced technology is rarely a single object. It is a network of capabilities. A simple metal screw can imply mining, refining, alloying, machining, measurement standards, tools harder than the screw, and the knowledge of threads. A semiconductor implies a civilization of purity, vacuum, optics, chemistry, and precision. On a generation ship, losing one industrial layer can make many higher layers impossible to replace, like a ladder with missing rungs between the floor and the roof. This is why designers may deliberately choose less advanced but more maintainable systems in some places. The most elegant component is not always the best if it requires an industrial ecosystem too fragile to reproduce. A slightly heavier, simpler pump that can be repaired in a modest workshop may be wiser than a perfect, compact device dependent on a vanished manufacturing technique. This principle feels almost old-fashioned, but in deep space, repairability becomes a form of beauty. The ship's industry must also manage information as carefully as matter. Blueprints, material specifications, process histories, failure databases, maintenance logs, software source code, scientific textbooks, training simulations, and design rationales must be preserved against radiation, corruption, obsolescence, and misunderstanding. It is not enough to store data. The ship must store readability. Formats must be maintained, translated, verified, and taught. Redundant archives may use digital, optical, magnetic, and perhaps physical etched records, but all of them require context. Future engineers must know why a certain alloy was chosen, why a tolerance matters, why a forbidden shortcut is forbidden, why a valve that looks oversized is actually protecting a rare failure mode discovered a century earlier. Knowledge loss is a mechanical hazard disguised as culture. If a society forgets the reason behind maintenance rituals, rituals can decay into superstition, or worse, into empty bureaucracy that still performs motions after meaning has gone. The healthiest generation ship would treat engineering education as civic education. Children would learn not only stories of Earth and stars, but the anatomy of the ship. How air moves, how water returns, how metal tires, how sensors lie, how error propagates, how redundancy can fail if common causes are ignored, and how every comfortable room depends on unseen work. The ship must also decide how much change to allow. Freezing technology at launch may simplify maintenance, but it risks stagnation and inability to solve new problems. Constant innovation may improve resilience, but it can introduce untested dependencies, software complexity, and incompatibility between old and new systems. A wise industrial culture would move slowly, testing changes in isolated sectors, preserving backward compatibility, and valuing proven repair over fashionable novelty. In this way, the ship becomes almost biological. It has bones, skin, nerves, metabolism, immune responses, scar tissue, memory, and regeneration. When something breaks, the goal is not merely to replace it, but to learn from the break, update the maintenance model, recover the material, retrain the crew, and reduce the chance that the same failure returns in a more dangerous form. Self-healing is not magic metal closing over a wound, though future materials may provide limited self-repair in coatings, seals, or composites. True self-healing is the coordination of detection, interpretation, fabrication, labor, and memory. It is the ship noticing pain and responding before pain becomes organ failure. And this, perhaps, is the most direct answer to how long a generation ship could really survive. It can survive only as long as its repair capacity remains at least as complex as its failure modes. If failures become more varied than the ship's ability to understand them, death begins. If manufacturing loses precision faster than systems degrade, death begins. If education weakens faster than machines age, death begins. If recycling loses key materials into inaccessible waste streams, death begins. But if the vessel can keep closing its loops, rebuilding its tools, renewing its knowledge, simplifying where complexity has become dangerous, and honoring maintenance as the central act of civilization, then time becomes less like a cliff and more like weather to be endured. In the long dark, the most heroic room aboard may not be the bridge with its windows facing impossible stars, but the workshop glowing softly at 3 in the morning, where someone machines a replacement part from recovered metal, checks it against an old specification, teaches a younger pair of hands how to feel a surface finish, and sends that small, humble piece back into the body of the ship. There, in the quiet discipline of repair, the generation ship learns the only lesson that can carry it across centuries. Nothing survives because it was built perfectly. It survives because it is allowed, again and again, to be made whole. The most fragile structure on a generation ship may not be the hull, or the reactor, or the rotating habitat, but the shared belief that the ship is still worth caring for. Because metal can be inspected, pipes can be pressure tested, crops can be replanted, and software can be restored from backups, while trust, once it begins to crack in a closed world, can spread through the corridors with a silence more dangerous than any alarm. A generation ship is often imagined as an engineering problem, and in one sense it is. But the longer the journey lasts, the more it becomes a human continuity problem disguised as engineering. The first crew may leave Earth with discipline, training, mission language, and a clear memory of oceans, weather, cities, mountains, and open sky. But their grandchildren may know Earth only through recordings, rituals, school lessons, and the careful emotional architecture of stories. By the fifth or sixth generation, the original reason for the voyage may no longer feel like a command from history. It may feel like an inherited condition, a fact of life as ordinary and unchosen as gravity. This is where society becomes part of the life support system. The air recyclers need technicians, but the technicians need meaning. The farms need workers, but the workers need dignity. The archives need preservation, but preservation requires a culture that believes the past matters even when the past is unreachable. If the ship is to survive for centuries, it cannot rely on permanent heroism, because heroism burns hot and briefly, while maintenance requires a cooler flame, the kind of steady civic patience that can be passed from parent to child without becoming resentment. On Earth, societies have often survived because failure in one region could be buffered by movement, trade, migration, outside resources, or the sheer geographical largeness of the planet. A generation ship has none of that spacious forgiveness. It is a sealed social ecosystem where politics, psychology, education, law, work, family, class, and technical reliability become tightly coupled. A dispute over food allocation is not merely social, it is metabolic. A failure in education is not merely cultural, it is mechanical, because untrained citizens cannot repair the machines that keep them alive. A breakdown in legitimacy is not merely political, it is atmospheric, because the people who no longer trust authority may not follow emergency procedures when the oxygen balance changes or a radiation storm warning arrives. The ship must therefore be governed as a world where every right and every duty has a physical shadow. Too much authoritarian control may keep order for a time, but it risks turning the vessel into a pressure chamber of fear, where people obey until the moment they no longer can. Too much freedom without shared limits may allow consumption, reproduction, conflict, or negligence to outgrow the ship's carrying capacity. The difficult center lies in a form of governance that is transparent enough to be trusted, firm enough to respect physical limits, flexible enough to adapt to new failures, and humble enough to admit uncertainty before uncertainty becomes disaster. Political science, in this setting, becomes applied systems engineering. A stable ship needs decision procedures for ordinary days and emergency days, for technical disputes and moral disputes, for population planning and resource rationing, for leadership succession and citizen consent, for scientific revision and cultural memory. It needs laws that can change without being casually rewritten by every passing crisis. And it needs institutions that preserve expertise without creating an untouchable priesthood of engineers. If only a small elite understands the reactor, the water system, the archives, or the navigation model, then knowledge becomes power in the narrowest and most dangerous sense. If everyone is told that all decisions are equally simple, the society may fall into comforting ignorance. The wiser path is distributed competence, where many citizens understand enough of the ship's anatomy to recognize false promises, respect real constraints, and participate in collective survival. Education aboard such a vessel would be deeper than schooling. It would be the ship teaching itself how not to forget. Children would learn mathematics not as an abstract ladder of tests, but as the language by which air pressure, rotation, crop yield, radiation exposure, and energy budgets remain understandable. They would learn history not only as the story of Earth, but as the story of why their ceiling is metal, why the stars outside do not move quickly, why certain doors are sealed, why water is never wasted, and why a broken valve can matter as much as an election. They would need beauty, too, because no society remains healthy on duty alone. Music, gardens, festivals, theater, quiet rooms, artificial seasons, games, art, and ceremonies of remembrance would not be luxuries in the shallow sense. They would be psychological infrastructure, ways of giving the mind a horizon when the body cannot step outside. A generation ship must manufacture not only oxygen, but belonging. Without belonging, the corridors become narrow, even if the habitat is large. The psychological environment would be unlike any human society on Earth. Though polar stations, submarines, isolated research bases, and long-duration spaceflight offer small fragments of comparison. Confinement, limited privacy, repetitive surroundings, dependence on life support, delayed communication, and the impossibility of leaving can magnify ordinary tensions. In a small crew, personality conflict is a mission risk. In a multi-generational ship, inherited narratives of conflict can become social geography. Families may remember old decisions differently. Professional groups may develop competing identities. People born in agricultural sectors, engineering sectors, medical sectors, or administrative sectors may slowly form cultural differences, even if the ship began with a unified mission. If access to comfortable space, fresh food, education, or reproductive permission becomes unequal, the ship may develop classes, and class aboard a closed system is not only morally troubling, but physically unstable, because no class can breathe separate air for long. The rich cannot escape the poor by moving to another continent. The powerful cannot build a private atmosphere independent of the neglected systems maintained by everyone else. The ship enforces interdependence whether society admits it or not. That interdependence can be a source of wisdom if made visible, or a source of bitterness if hidden behind hierarchy. Another danger is mission drift, the slow alteration of purpose. The first generation may define survival as reaching another star. Later generations may define survival as preserving the ship itself. Still later generations may question whether arrival is desirable at all. If the destination is a planet, will the ship-borne people want to descend into gravity? Weather, microbes, open space, and an uncontrolled sky. If the destination proves unsuitable, will the society accept a new plan? If navigation data changes and the original promise becomes impossible, how does a culture built around arrival survive disappointment? These questions sound philosophical, but they are practical. A society unable to revise its purpose may break when facts change. A society with no purpose beyond comfort may neglect the disciplines that keep comfort possible. The healthiest generation ship would likely carry layered meanings: a scientific mission, a duty to descendants, a reverence for life, a commitment to truth, and a flexible understanding that reaching a star is not the only measure of not having failed. Communication with Earth, if possible at all over interstellar distances, would become delayed, faint, and eventually historical. Messages might take years, decades, or longer, and the farther the ship travels, the less Earth can function as a real-time authority. This delay creates adulthood. The ship must become morally and politically self-governing while still deciding how to remember the planet that built it. Earth may become homeland, myth, archive, burden, promise, or ghost. The emotional handling of that memory matters. If Earth is treated as paradise lost, ship-born generations may feel condemned to a lesser world. If Earth is dismissed as irrelevant, the society may sever itself from the larger human story. If Earth is remembered honestly, as beautiful, flawed, generous, and gone from reach, then memory can become nourishment rather than wound. The same care must be given to mortality. Every person aboard knows, or eventually learns, that they may not see the destination. The society must give meaning to lives lived entirely in transit, or else the voyage becomes an inheritance of postponement. A child should not grow up feeling like a bridge that matters only because someone later may cross it. Life aboard must be complete in itself. Friendships real, work meaningful, love honored, curiosity encouraged, grief held gently, and ordinary days allowed to be ordinary. In this sense, the ship's survival depends on refusing to treat its people as cargo for the future. They are the future, already alive. The vessel cannot ask generation after generation to sacrifice everything for arrival, while giving them no reason to cherish the journey. This is where the long night becomes almost sacred. The ship must create mornings without a sunrise, seasons without a planet, community without open land, and hope without certainty. It must teach discipline without crushing tenderness, preserve truth without becoming cold, and maintain order without forgetting that human beings need more than efficient systems. The final vulnerability is not rebellion in the dramatic sense, but quiet disengagement. Citizens who stop believing maintenance matters. Students who memorize procedures without understanding. Leaders who hide bad news to preserve calm. Technicians who skip inspections because nothing failed last time. Families who no longer feel that the ship belongs to them. Against that slow erosion, society must renew itself deliberately, as the farms renew air and the recyclers renew water. It must hold public memory of past failures, celebrate repairs as victories, teach the ship's limits without turning them into despair, and allow enough voice that obedience grows from trust rather than fear. A generation ship can survive metal fatigue if it knows where the cracks are. It can survive social fatigue only if it has ways to speak before silence hardens. So the answer to how long it can live is partly political, partly psychological, partly poetic. It can live as long as its people remain a people, not merely a population. It can live as long as knowledge remains shared, work remains dignified, limits remain understood, and the unborn are treated not as abstract mission goals, but as future neighbors in the same fragile home. Somewhere in the deep dark, long after the departure generation has become names in the archive, the ship may still be alive. Because a teacher explains a pressure equation to a tired child. A council tells the truth about a failing system. A farmer saves a seed line. An engineer admits uncertainty. A song is sung at the end of an artificial winter, and thousands of people remember, in their own quiet ways, that the vessel is not carrying society through space. Society is carrying the vessel through time. To answer how long a generation ship could really survive, we have to walk through time as if the ship itself were aging in front of us. Not in a single dramatic leap from launch to destination, but in widening rings of possibility. 50 years, 250 years, 1,000 years, and then the colder, stranger question of whether longer still means living or merely drifting. At 50 years, the ship is still close to the psychological shadow of Earth, because the oldest people aboard may remember the launch. The design language of the original builders is still readable without translation, and many of the first-generation systems may still be operating within lifetimes that engineers can imagine, test, and certify with some confidence. A 50-year survival window is difficult, but it is not yet the full generation ship problem. It resembles an extreme extension of known aerospace, naval, nuclear, ecological, and closed habitat engineering. The ship can still rely heavily on stocked reserves, oversized margins, replaceable components packed before departure, original training traditions, and a social mission that feels emotionally near. If the vessel carries enough food production, water recycling, medical capacity, spare parts, and power redundancy, half a century is a brutal but conceptually recognizable challenge. The most dangerous failures in this window would be early design mistakes. A radiation model that underestimated exposure. A farm system less stable than predicted. A reactor subsystem that ages faster than expected. A materials flaw hidden in a batch of critical parts. A governance structure that works beautifully in simulations but poorly with tired human beings. In this first scenario, the ship survives if its launch assumptions were conservative and its crew is still close enough to the founding culture to interpret those assumptions correctly. But 50 years does not prove the ship is a world. It only proves that the first candle has not yet burned through its reserve of wax. At 250 years, the question changes completely, because no one alive remembers Earth except through inherited memory, archives, rituals, recordings, and the emotional climate created by generations of teaching. The ship is now old in the way cathedrals, empires, languages, and scientific institutions become old. It has passed beyond the warranty period of nearly every complex machine built by the original civilization. Its first spare parts have been used, its second-generation repairs have themselves become objects needing repair, and the original mission documents may now require cultural interpretation, not merely reading. A 250-year ship must have crossed the threshold from storage to regeneration. It cannot simply consume reserves. It must manufacture, recycle, educate, and govern itself with enough competence that the founding generation becomes important but no longer necessary. This is where maintenance becomes history, and history becomes engineering. A pump replaced in year 70 may fail in year 160, and the replacement for that replacement may be built by people who know the Earth oceans only as blue motion in old video. A crop variety chosen by launch agronomists may have adapted to shipboard conditions, or weakened under narrow breeding, or been replaced by a more resilient line developed aboard. The population may have grown, stabilized, or shrunk, and each path has consequences. Growth stresses food and energy. Stability demands careful reproduction and cultural discipline. Decline threatens skill diversity and genetic breadth. At this scale of time, small annual inefficiencies become major forces. A 1% material loss in a critical recycling stream is not small across centuries. A slight bias in educational prestige, where children prefer governance or art over difficult maintenance trades, can become a technical shortage. A subtle erosion of trust in institutions can turn every emergency procedure into an argument. A 250-year generation ship therefore survives only if it has become a layered society, not a permanent emergency crew. It needs schools that teach physics as civic knowledge, farms that function as both food systems and ecological laboratories, workshops capable of making not just parts, but tools, and laws that can handle the unsettling fact that most people aboard never chose the mission, yet depend on it for every breath. The ship that reaches 250 years still alive has proven something far more impressive than endurance. It has proven cultural metabolism. It has learned to turn children into caretakers without reducing them to instruments. It has kept enough meaning alive that the walls are not merely confinement. At 1,000 years, the problem enters a realm closer to deep history than engineering schedules, because a millennium is long enough for languages to shift, myths to form, institutions to rise and harden, technologies to be forgotten and rediscovered, and the original destination itself to become a question rather than a certainty. A 1,000-year ship is not a long mission. It is a moving civilization whose founding event has become ancient history. The physics of survival is still present, but now it is braided with archaeology, anthropology, ecology, and the psychology of inheritance. The power system must not merely have lasted, it must have been renewed multiple times. The industrial base must not merely have repaired components, it must have preserved entire chains of production. The life support ecology must not merely have remained balanced, it must have passed through disease events, genetic changes, crop replacements, microbial shifts, and unknown, long-cycle feedbacks without crossing an irreversible threshold. The archive must not simply exist, it must still be trusted, readable, and connected to practice. A millennium also forces humility, because the ship may encounter problems that no launch simulation could honestly predict. Materials exposed to radiation, vibration, thermal cycling, and repair histories may develop failure modes no one named at departure. Social structures that once prevented chaos may become oppressive if they cannot adapt. Energy reserves that looked enormous may begin to show their finite nature if the ship has not developed a reliable long-term fuel cycle. Artificial ecosystems may drift into new equilibria that are stable but nutritionally or psychologically poorer. The crew may decide that arrival is no longer the purpose, or that the ship itself is the only homeland, or that the destination selected 1,000 years earlier is no longer suitable based on improved observations. In such a scenario, survival means more than preventing death. It means preserving decision-making capacity. A 1,000-year generation ship must be able to revise its own story without losing its will to live. It must be conservative enough to maintain vital systems and imaginative enough to solve problems its founders did not foresee. This is a rare combination even on Earth, where civilizations are buffered by oceans, minerals, weather, trade, and migration. Inside the ship, there is no outside reservoir of forgiveness. 1,000 years would likely require a vessel so large, redundant, and industrially capable that it approaches the idea of a world ship. Thousands or tens of thousands of people, heavily shielded living regions, rotating gravity, multiple reactor systems, or a long-lived fusion-like energy economy. Deeply protected biological archives, broad genetic diversity, flexible agriculture, full material recycling for most critical elements, and a culture that honors repair as a central moral act. Even then, the number 1,000 should not be spoken like a guarantee. It is a possibility at the edge of disciplined design, not a promise written into the stars. Beyond 1,000 years, the word survive begins to divide into categories. A dead hull could survive physically for millions of years if nothing large strikes it, because vacuum and cold can preserve certain materials in strange ways. A minimal remnant population might survive biologically, while losing the scientific, industrial, or cultural complexity needed to remain a true world. A highly successful ship might become self-sufficient enough to continue for several thousand years, but only if it has solved not one problem, but the full family of compounding problems: energy renewal, material closure, radiation protection, ecological resilience, genetic breadth, social legitimacy, technical education, and the emotional meaning of life in transit. The longer the timeline, the more the limiting factor moves away from any single machine and toward coupled systems. If the energy system fails, ecology fails. If ecology fails, population fails. If population fails, maintenance fails. If maintenance fails, shielding, farming, water, medicine, and archives fail. If meaning fails, all of the above become harder before the instruments show danger. This coupling is what makes the generation ship both possible in principle and unforgiving in practice. It is not one chain, it is a web. And the strength of the web depends on whether damaged strands can be repaired before stress moves elsewhere. So the survival scenarios can be imagined like layers of night. In the first night, lasting decades, the ship lives on launch quality, reserves, redundancy, and the living memory of Earth. In the second night, lasting centuries, it lives on regeneration, education, and the ability to replace the builders with descendants who understand the builder's work. In the third night, lasting a millennium, it lives only if it has become a civilization capable of renewing its machines, its ecosystems, and its purpose. And beyond that, in the very long dark, survival becomes less like a voyage and more like planetary stewardship without a planet. The ship can no longer think of itself as crossing space in the ordinary sense. It must think of itself as a small Earth that happens to be moving. The honest final estimate is therefore conditional rather than absolute. A modest vessel with partial recycling might last decades. A serious generation ship with strong life support and repair capacity might last a few centuries. A true world ship with deep redundancy, large population, closed material cycles, protected biology, and self-renewing industry might reach 1,000 years or more. But the farther we push the number, the more we are asking not whether a machine can be built, but whether a whole way of living can remain intelligent, careful, and generous under a sky that never changes. Somewhere between year 50 and year 1000, the generation ship either stops being a vehicle and becomes a world, or it becomes a beautiful corridor of failures, waiting for the last light to go out. And if one ever does survive long enough for distant stars to grow brighter through its forward windows, it will not be because it outran time, but because, night after night, century after century, its people learned how to pay time's price without letting the world inside grow smaller. The final answer is that a generation ship could survive in deep space for decades if it is only an enlarged spacecraft, for centuries if it becomes a disciplined closed habitat with strong repair capacity, and perhaps for 1,000 years or more only if it crosses the most difficult boundary of all and stops being merely a ship, becoming instead a small world with its own metabolism, memory, industry, and moral order. That is the answer in its plainest form, but it is not a simple answer, because the lifetime of such a vessel is not controlled by one heroic technology, one powerful engine, one perfect shield, or one elegant equation. It is controlled by the relationship between all of them, by whether the ship can keep its losses smaller than its renewals, its errors smaller than its corrections, and its social fractures smaller than its shared purpose. In the language of physics, the ship is a local pocket of low entropy, surrounded by a universe that does not hate it, does not notice it, and does not need to hurry. The dark between the stars is patient. It can wait for a bearing to wear down, for a crop disease to adapt, for a reactor component to age, for a school to stop teaching one difficult skill, for a political institution to hide one inconvenient truth, for one critical material to become trapped in waste streams no one can fully recover. The generation ship survives only while it can answer that patience with a deeper patience of its own. At the lowest level, survival is a balance of energy. The vessel must keep producing enough usable power to run life support, agriculture, computation, medicine, manufacturing, heating, cooling, circulation, lighting, communications, navigation, and the quiet background work of measurement. Without that continuous flow, oxygen becomes chemistry without motion. Water becomes a stored substance instead of a cycle. Food becomes memory instead of harvest, and the ship slowly approaches the same cold equilibrium as the space around it. But energy alone is never enough. A reactor can glow steadily for a long time and still fail to preserve a civilization if the water loop loses trace elements, if the farm ecosystem drifts into fragility, if the radiators cannot reject waste heat, if the electronics become unreadable, or if the people entrusted with the system no longer understand what they have inherited. So the better way to think about the final answer is not how many years can the ship last, but how many essential loops can it close and how many times can it reopen them after failure. A short-lived ship survives by storage. A longer-lived ship survives by recycling. A true world ship survives by regeneration. Storage says, we brought enough. Recycling says, we can use it again. Regeneration says, we can recover, remake, relearn, and continue, even when the original plan has been damaged by time. That third state is what separates an interstellar arc from a very large coffin. If the ship has only packed food, water, oxygen, and spare parts, its survival is limited by inventory, and even enormous inventory is only a countdown written in mass. If it has strong recycling, it can stretch the countdown, but every imperfect cycle still leaks future into waste. If it has a nearly closed ecosystem, it begins to resemble Earth in miniature. Yet a miniature Earth is not automatically stable because small systems have fewer buffers, faster feedbacks, and less room for forgotten mistakes. If it has self-renewing industry, it can replace parts rather than merely spend them, but that industry must itself be maintained, powered, supplied, audited, and taught. If it has a healthy population, it can reproduce bodies, but it must also reproduce skill, judgment, trust, and meaning. The most advanced design, then, would be a layered organism. Outer shielding to soften radiation and impacts, water and stored mass arranged as protective geography, rotating habitats to give bodies a reliable down, farms and bioreactors to turn energy into food and breath, industrial workshops to rebuild the ship from its own worn materials, redundant power systems to prevent a single heart from becoming a single failure, medical and genetic archives to preserve biological breadth, and a culture that treats maintenance not as background labor, but as the central ritual of staying alive. Such a ship might survive several centuries with plausible extensions of known principles, though building it would remain far beyond anything humanity has yet demonstrated as a complete system. To reach 1,000 years, it would need more than engineering confidence. It would need civilization-level continuity. It would need children born in year 400 to understand why a valve designed in year 0 matters, and citizens in year 700 to trust records written by people whose language, customs, and fears may feel ancient. It would need archives that remain readable, schools that remain rigorous, leaders who do not confuse secrecy with stability, and repair traditions that preserve reasons, not just procedures. A 1,000-year ship cannot depend on a frozen culture, because frozen cultures become brittle. It cannot depend on endless innovation either, because careless innovation can introduce failure faster than it solves it. It must practice slow adaptation, the way a forest changes while remaining a forest, or the way a living body replaces its cells while still being recognizably itself. This is why the final answer carries both wonder and warning. In principle, no known law of physics appears to forbid a generation ship from surviving for many centuries, provided the vessel is large enough, shielded enough, powered enough, ecologically resilient enough, industrially self-sufficient enough, and socially wise enough. But the phrase, in principle, is a quiet door with a long hallway behind it. It means the mathematics does not laugh at the idea, not that the workshop can build it tomorrow. It means survival is not impossible, but conditional. It means the ship must be designed not for the best year or the average century, but for the bad era. The era of damaged radiators, reduced harvests, political exhaustion, aging reactors, demographic imbalance, and a generation that asks whether the destination still matters. The literal answer is therefore a spectrum. A modest vessel with partial recycling might keep people alive for decades. A serious generation ship with regenerative life support, large reserves, conservative power margins, and a strong repair economy might plausibly endure for a few centuries if luck and governance hold. A vast world ship, closer to a moving island than a spacecraft, with thousands or tens of thousands of people, deep material closure, full-scale manufacturing, protected biological libraries, robust artificial gravity, and a culture trained for truth over comfort, might extend survival into the realm of a millennium or more. Beyond that, the uncertainty expands until the question becomes less like aerospace engineering and more like planetary history. We can imagine survival for several thousand years under extremely favorable conditions, but every additional century increases the demand for renewal, and no honest answer should pretend that a system of machines, ecosystems, and human beings can be guaranteed across such distances of time. A dead hull may last far longer than its people. A simplified remnant society may remain alive while losing the technical power to reach its original destination. A successful world ship may decide that arrival is not the only meaning of the voyage. These possibilities matter because survive is not one word. Does it mean the hull remains intact? Does it mean human bodies remain alive? Does it mean a healthy civilization remains capable of science, memory, choice, and expansion? The deepest version of the answer must choose the last meaning, because a generation ship that preserves breathing but loses understanding has survived only in the thinnest biological sense. The goal is not merely to keep hearts beating in the dark. It is to keep a human world wide enough to think, repair, love, doubt, learn, and decide. This is why the generation ship is such a powerful idea. It compresses every question of civilization into one vessel. How much energy do we need to remain free? How much ecology do we need to remain alive? How much diversity do we need to remain human? How much memory do we need to remain wise? How much humility do we need to survive our own technology? The ship asks all of these questions without raising its voice. It drifts through the black, and inside it, a child learns the names of elements. A farmer checks root chemistry under violet light. An engineer listens to a pump. A doctor studies radiation records. A teacher explains why Earth was not a myth. And somewhere near the center, behind layers of water and metal and growing things, the archive waits like a second heart. If that world can keep renewing its loops, it may live long enough for the stars ahead to become more than points of light. If it cannot, then distance will not be the thing that defeats it. Time will. Not time as a calendar, but time as wear, drift, forgetfulness, and the quiet multiplication of small debts. And so the final answer is this. A generation ship could survive in deep space as long as it can remain more like a planet than a machine, more like a culture than a mission, more like a living ecosystem than a sealed container. For decades, machines may be enough. For centuries, repair and recycling must join them. For 1,000 years or more, only a world can endure. And perhaps that is the most beautiful and humbling truth of the whole journey. To cross the emptiness between stars, humanity would first have to learn how to carry a small, patient Earth inside the dark, and keep it gentle, intelligent, and alive until the future finally opens its eyes. Thank you for spending this quiet journey with me. A generation ship may seem like science fiction, but it also asks one of the deepest questions of all. How long can humanity keep a small world alive in the dark? If you enjoyed this video, thank you for listening, and I hope you rest well tonight.